I'd like to review a little bit of Coulombs law. Coulombs law here, force of electricity, electric force is K times Q1 times Q2 over D squared. This tells us the force between any two charges, and it's a pairwise function, so we can only do two charges at a time. As an example of this, let's look at a charge configuration that's set up in a triangle. Let's set up something that looks like maybe an isosceles triangle with some different charges. Let's put, let's say 5 microcoulombs up here, maybe 2 microcoulombs down here, and let's say 10 microcoulombs down here. And let's separate these charges equilaterally, so maybe let's say 10 centimeter separation for each of these. 10 centimeters and 10 centimeters. So this makes our geometry a little bit easy because we know it's equilateral, so we know something about the angles for later on. So in order to do this, the typical question in this case would be, what's the force on these fixed charges because of the other two charges? So what's the force on the 5 microcoulomb charge because of the 2 microcoulomb charge? What's the force on the 5 microcoulomb charge because of the 10 microcoulomb charge? And then combine those vectorially. So let's just do that for the 5 microcoulomb charge and see what happens, and then we can work our way through. So to start with, we always want to do a free body diagram. So here's the 5 microcoulomb charge. And we know that the force because of the 2 microcoulomb charge is going to be repulsive, so there's going to be a force up in that direction. That's going to be the force between the 2 and the 5. And then the force between the 5 and the 10 is going to be attractive, so we're going to have a force down in this direction. That's going to be the force between the 5 and the 10. All right, so we have these two forces. We use Coulomb's law, KQQ over D squared, in order to figure out the magnitude of those forces. So we would just say force between the 2 and the 5 is K times Q2 times Q5 over the distance squared. So 9 times 10 to the 9th newtons meters squared per coulomb squared. We like to keep those units in there to remind us that we want meters and coulombs. So the 2 is a 2 microcoulombs, so we need 2 times 10 to the minus 6 coulombs in order to make sure we're in the right units. And we want 5 times 10 to the minus 6 coulombs to make sure we're in the right units. And then we divide that whole thing by the distance squared, and since our universal constant is in meters, our distance, which is 10 centimeters over here, we have to convert that to meters, or 0.1 meters. So we want 0.1 meters squared. All right, so we plug that all into our calculator. 9 times 10 to the 9th times 2 times 10 to the negative 6 times 5 times 10 to the negative 6 divided by 0.1 squared, and we get the force between 2 and 5 is equal to 9 newtons. We can do the same thing, the force between the 5 and the 10. Okay, Q5, Q10 over the distance squared, and the same process. 9 times 10 to the 9th newtons meters squared per coulomb squared. 5 times 10 to the minus 6 coulombs. 10 times 10 to the minus 6 coulombs over the distance, which equilateral, so this distance again is 10 centimeters, or 0.1 meters squared. And we plug that into our calculator. 9 times 10 to the 9th times 5 times 10 to the negative 6 times 10 times 10 to the negative 6 divided by 0.1 squared, and we get 45 newtons. Okay, so we see that we know the two forces, and we have some directions here, so we just have to combine those vectorially. So we have to think about what that means. Generally, when we have things that are in vectors like this, we're going to just draw in, here's my coordinate system in my x direction and my y direction. I'm going to break these vectors up into x and y coordinates, or x and y components, so that then I can combine the components independently. So if this is my, I'll do that independently, so if this is my, for the force between 2 and 5, this is 9 newtons, and I'm going to break that up into a horizontal component and a vertical component. I have to know what the angle is, and that angle is going to be 60 degrees. We can pick that up from the geometry over here. This guy here, this internal equilateral triangle, 60 degrees, 60 degrees, 60 degrees, so we can pull that off the geometry. Let's see, maybe we want to see that. If I know this is 60 degrees, if I just extend these lines, I also know that this has to be 60 degrees, so these are equal angles because they're opposite. So if that's 60 and 60, that's 120. I know that these also, if I want to bisect this, right, you can see that that's equal, so that's another 60 here and another 60 here. So basically everything we're doing is in terms of 60s here. So this becomes a 60-degree angle. So this is going to be 9 times the cosine of 60, and this is going to be 9 times the sine of 60. And so we say 9 cosine 60 and 9 sine 60. So this is going to equal to 4.5 newtons, and this is going to be 7.79 newtons. So I know the components there. We can do the same thing, force between the 5 and the 10. We end up with something in this direction, 45 newtons. And again, we want to break that up into a horizontal and a vertical component. Again, this is a 60-degree angle, so this is going to be 45 cosine 60, 45 sine 60. Plug that into the calculator, and we get 22.5 newtons and 38.97. Make sure that looks like a 3 newtons. Okay, so we have our components. Now to combine them, we just combine them independently. So I'm going to add these guys together. So horizontally, I get 4.5 plus 22.5, which is 27 newtons. And vertically, I get 7.79, and then I get minus 38.97. Right, this one is going up, so it's plus. This one's going down, so it's negative. So that's going to be 31.18, let's say 31.2 newtons down. So those are my components of my answer. And then I can turn around and say, how do I put that together into a vector format? Well, I just put it back into a vector. 27 newtons in the horizontal direction, minus 31.2 newtons in the vertical direction. And so my resultant, my ultimate resultant, is going to be something that looks like this. And I just use Pythagorean theorem. 27 plus 31.2 squared, and then root the answer, and I get 41.3 newtons. And then I would also want to know what this angle is, and that angle, I could just use my favorite trig function. That angle could be the inverse tangent of 31.2 over 27, or 31.2 over 27, 49, let's say 49.1, so let's say 49 degrees. So my final result, if I'm looking for what is the force on the 5 microcoulomb charge, It's being pushed up by the 2. It's being pulled down by the 10. But the 10 is much bigger, so it's going to have a bigger effect. We're going to end up with a 41.3 Newton force pulled down at an angle of 49 degrees below the horizontal. So that's one example of just finding the force on the 5. If you would like to find the force on the 10 or force on the 2, we could do the same thing. So let me just pull out, and we'll at least draw out those vectors. So let's see what happens here. If I say, let's find the force. Here's a free body diagram for the 2 microcoulomb charge. Right? 2 microcoulomb charge is going to be repelled by the 5. So we're going to have a force in this direction. That's going to be the force between the 2 and the 5. And then it's going to be attracted by the 10. So it's going to be going this way, and that's going to be the force between the 2 and the 10. So again, what we would do is we'd say, what's the force between the 2 and the 5? K Q2 Q5 over d squared. And we'd say, what's the force between the 2 and the 10? K Q2 Q10 over d squared. And here's where we start saving ourselves some time. If I'm looking for the force between the 2 and the 5, I already know the force between the 2 and the 5 because I did that earlier, right? I did that for the 5, and since it's a pairwise function, that's going to immediately equal 9 newtons again. So I saved myself a bunch of time. This one is going to be 9 times 10 to the 9th newtons meters squared per coulomb squared. 2 times 10 to the minus 6 coulombs. 10 times 10 to the minus 6 coulombs over 0.1 meters squared. So we're going to end up with 9 times 10 to the 9th times 2 times 10 to the negative 6 times 10 times 10 to the negative 6 divided by 0.1 squared. We're going to end up with 18 newtons. And then we can quickly go through the vector format again. I noticed that this force between 2 and 10 is already in the horizontal direction, so I don't have to do any decomposition for that. Force between the 2 and the 5 I have to break up, but again, I already broke that up. If I look here at this 9 newtons, I broke it up into 4.5 newtons and 7.79 newtons. The only difference is going to be I'm going to break it up in the other direction, right? So I'm going to say, instead of 9 newtons going up over here, I'm going to say 9 newtons going down, which means it's going to break up into a vertical component and a horizontal component, and that vertical component is going to be negative 7.79, and the vertical component is going to be negative 4.5 newtons. So I just saved myself a bunch of time by using the work that I've done earlier. Okay, so this is the 9 newtons, and I know that the force between 2 and 10 is 18 newtons. So horizontally, I end up with 18 newtons to the right minus 4.5 newtons to the left, which is 1312.5 newtons to the right. And vertically, I end up with just the minus 7.79 newtons. And then I put that back together again so that I can say 12.5 newtons, 7.79 newtons, and then I have to make the resultant 12.5 squared plus 7.79 squared square root using Pythagorean. So this is going to end up being 14.7 newtons, and the angle, again, theta, is going to be the inverse tangent of 7.79 over 12.5, or the angle is going to be, let's see, inverse tangent of 7.79 divided by 12.5. Angle is going to be 31.9 degrees, and again, that's this theta below the horizontal. right? So you might think, oh, that seems kind of weird, right? And this angle is pulling to the right. And looking back at my original picture, I thought I was going to pull down and to the right, but that just means that this force 210 is bigger, right? It's 18 newtons, so I'm pulling a much bigger force to the right. So if I wanted to draw this arrow to scale, I would have to say, oh, this is twice as big. I'm pulling it out here, twice as big. So now if I combine these two vectors, I will end up with that red vector that looks something like this, right? 14.7. That's going to be my resultant. So you can see how using Coulomb's law and vector addition gets us to what we want. So the only one left to do would be the force on the 10 because of the 5 and the 3, and I'll leave that one to you.